we'll be presenting the utility fit look-ahead agent for sequential multi-deal negotiation. This work was done by me, Garrett Seo, Nguyen, and Xintong Wang. Briefly, in sequential multi-deal negotiation, there is a center agent that encounters multiple edge agents in a sequence. And each edge will be denoted as a sub-negotiation between a center and edge agent where it will follow a bilateral alternating offers protocol. The center agent will be rewarded for a combination of all agreements in the sequence. A little closer look into sub-negotiations. If we let omega denote the outcome space, then we could denote omega sub I as the sub-outcome space for the ith sub-negotiation. So this omega will be just equal to the Cartesian product of all these sub-outcome spaces. What we're given is the utility function that maps omega, so some outcome in omega, some final outcome to a real number. But what's the utility for realizing some sub-outcome in some subspace for a sub-negotiation? Or in other words, at each sub-negotiation, what is the best agreement? Naively, we can always underestimate this utility for some sub-outcome. What we can always do is we could just pretend or assume that we'll do our worst, and we'll always have a disagreement in future sub-negotiations, as shown by the none appended for the rest of the history. However, can we do better than this naive underestimation? Our approach will be to divide the center strategy in two parts. One is this idea of look-ahead planning to estimate the utilities of these sub-outcomes, and when these sub-outcomes or outcome space becomes too large, we'll employ early termination. Then our conceding strategy. How can we get the offers that we want the best at each sub-negotiation? And we'll do this via utility fit. Trian will now present the look-ahead planning.
The outcome space is a tree. So take a node at depth I. This is the beginning of sub-negotiation I. And it contains the sub-outcomes as its state from the previous sub-negotiation 0 through I minus 1. Its children represent all the sub-outcomes that are possible in the sub-negotiation, right? So U1, U2. And what we want to do is we want to calculate the expected or estimated utilities of these sub-outcomes. How we do this is through a recursive process. And so we calculate the expected utility of all its children. Then we assign probabilities to those children, which is essentially the probability that if we propose a sub-outcome, what probability will be accepted. We estimate this probability based on if we believe the other agent to be cooperative or adversarial. And then we propagate the expected utility upwards. So a big problem we ran into was that the number of outcomes can soon become intractable because it's exponential in size, right? It's a tree. And so we need to perform an early termination somewhere. So essentially what we're doing is when we're searching down the tree, we're going to stop at some depth k. And then instead of calculating by calculating the expected utility of its children, since we stopped at the depth, we use a naive underestimation heuristic, which was given to us by the Python package known as the SideUFun, where we take the state of all sub-negotiations that have happened, and then we assume that no future negotiations will reach agreement. And so this is what we use as our heuristic and our base to start propagating up.
We will now go into our concession strategy. We're first going to assume that the opponents will follow a time-based strategy. Whereas time goes on without reaching an agreement, the opponent will begin to offer bids of decreasing utility for themselves, where they start at some maximum utility and will concede to some minimum utility. For our concession strategy, we're going to take advantage that there is no discount in this problem. So we will delay the negotiation as long as possible. And the reason is that we want to make the most informed bid at the last time step. And we'll get this information from the opponent offers. But how do we use this information? As the opponents concede over time, they're going to offer bids of decreasing utility. We're also going to make the assumption that the opponent is adversarial. So as the opponent's utility decreases, our utilities will increase. We're going to map the opponent offers to our estimated utilities that we employed from the look-ahead. And what we should see is that our estimated utilities should increase with time according to the bids that they are offering. And we'll use the opponent offers to map to our utility to fit some kind of utility curve. More specifically, this utility fit will follow a parametric function, this x prime, which will represent our estimated utility from the opponent's offers. It will take in two parameters, a u sub max, which will be the maximum utility that the opponent is willing to concede to, and beta, the opponent's concessive degree. The idea is we'll find the parameters that best fit according to their offers, and at the final time step, propose an outcome with estimated utility at the final time step, t equals 1. To the right is an example of the utility fit being employed within a sub-negotiation. This wraps both our conceding strategy and our look-ahead strategy for the utility fit agent to do its best in sequential multi-deal negotiation.